High-dimensional data is everywhere: genomics, cybersecurity logs, financial records, sensor networks. The more complex the system, the more features we have to analyze. But here's the problem. As dimensionality increases, traditional anomaly detection methods start to break down. The relationships between features become harder to interpret, distances between points lose meaning, and even normal data points start looking like outliers. This phenomenon is known as the Curse of Dimensionality, and it presents a major challenge for models like isolation forest. In low-dimensional data, random partitioning works well. Isolation forest selects features, makes splits, and anomalies get isolated quickly. But in high-dimensional space, splitting randomly across all features can become less effective, because many of those features may not be relevant to detecting anomalies. As a result, anomalies don't necessarily get isolated as fast as they should, reducing the model's ability to distinguish them from normal points. One way to address this issue is feature selection, reducing the number of features before applying isolation forest. Not all features contribute equally to anomaly detection. Some may be noisy, redundant, or completely irrelevant. Techniques like recursive feature elimination, RFE, lasso regression, or mutual information scoring can help identify the most important features, improving the model's accuracy by focusing on what actually matters. Another approach is dimensionality reduction. Methods like principal component analysis, PCA, or TSNE transform the dataset into a lower dimensional space while preserving its structure. PCA, for example, creates new features that capture the most variance in the data, helping isolation forest focus on the most informative patterns rather than getting lost in noise. By applying PCA before running isolation forest, we can often improve anomaly detection performance in datasets with hundreds or thousands of features. A third strategy is adjusting model parameters. In high-dimensional datasets, lowering max features, the number of features considered at each split, can prevent the model from relying too much on irrelevant attributes. Instead of randomly selecting from all available features, reducing max features forces the model to focus on a smaller subset of the most relevant ones, increasing the chance of isolating anomalies efficiently. Another technique is combining isolation forest with other models. Hybrid approaches can improve accuracy by leveraging multiple anomaly detection methods simultaneously. For example, isolation forest can be used alongside one-class SVM or local outlier factor, LOF, to validate results and increase robustness, especially in high-dimensional spaces where a single model might struggle. But let's be real. High-dimensional anomaly detection is always a challenge. The key is to strike a balance between preserving important information and reducing noise. If we reduce dimensions too aggressively, we might lose critical signals. If we don't reduce them at all, the model might struggle to differentiate anomalies from normal variations. That's why experimentation is crucial. Testing different feature selection methods, tweaking parameters, and combining techniques to find the best approach for each dataset.